Good morning. Today is January 24th, 2012. This is the continuation of the 9-1 lecture. We've got a lot to do, so we're going to jump right in. We finished yesterday, not quite finished, we left off yesterday with this idea of something called the null hypothesis and the alternate hypothesis. And through multiple demonstrations, I try to get you to understand the null hypothesis really is a statement of something that we don't believe in. It's a supposition. It is a unsupported claim. And that this thing called the alternate hypothesis actually represents the thing that we do believe is true. In the previous example, we said something like, I claim that I'm an 80% shooter. Jason, who's not here, didn't believe me. He said, no, I don't believe you. I think you're less than an 80% shooter. But in order to prove that I'm not an 80% shooter, he is temporarily going to believe that I am an 80% shooter, using that number to find some probability, and that probability, if it is low, and I'm being vague here about what I mean by low, if it is low, that low probability is going to be evidence against the claim that I'm an 80% shooter. If you're an 80% shooter, you would never only shoot 32 of 50 shots. Make 32 out of 50. So, we start with this very, very strange thing. The null hypothesis is a claim that's unsupported, and it's actually not what we believe. We actually believe the alternate hypothesis. Once we show the null hypothesis to be null, meaningless, not true, we can replace what we think is true, and that is that I'm less than an 80% shooter. So, let's go through the variations that can happen in this situation. When we write a null hypothesis, it takes this general form. It's some parameter is equal to some value. In the statement that I just made, the parameter was P, a population proportion, equals. And what did we say we didn't think was true? That Fedor is an 80% shooter. We don't think that's true. That's why we're proposing it as the null hypothesis. Well, the alternate hypothesis could indeed be that I'm greater. The alternate hypothesis could be that I'm worse. Or the alternate hypothesis could be, I don't know whether you're better than worse, but you're not exactly 80%. Now, the first two versions of the alternate hypothesis are referred to as one-tailed tests. The third version, the one with the not equal sign, is referred to as a two-tailed test. Okay? Let's go through that idea. We say an alternate hypothesis is one-tailed or one-sided if it states the parameter is larger than or smaller than some value. The value that's listed in the null hypothesis. They're referring to that value as the null value. Now, one-sided or one-tailed may be a strange expression for you. But I want you to picture that we're going to be pulling these probabilities out of a normal distribution. And if my statement is that I'm actually a greater shooter than 80%, I may use the probability that's only in that one-tailed. So we'll call it a one-tailed or a one-sided test. Danny? Oh, I think I put it in your hanging folder. Why don't you look in there? Is it in there? Great. All right. If the alternate hypothesis is two-tailed, or is a not equal sign, we will get the probability associated with that by taking the probabilities in both an upper and lower tail. And it might suggest that the two-tail test, actually the probabilities when we calculate them are always, or nearly always, twice as big as the single tail, because of the symmetry of the normal distribution. So, the null hypothesis always has an equal sign. It's always some parameter is equal to some value. The alternate hypothesis is some form of not being the same, either greater than, less than, or simply not equal. Are you okay with that idea? Does anyone need more time on this slide? Megan needs more time. Not a problem. I will drink some tea. Okay. Tell me when we're ready, Megan. Ready? Okay. Okay, a couple other notes here. The hypotheses that we're talking about are always statements about the population. Remember, we're in this section called inference. We're always trying to make statements about what's going on at the population level, not about what's going on at the sample level. Okay? So it would be incorrect to say as a null hypothesis that p hat is equal to 0.64. P hat is a statistic. It's about a sample. Hypotheses are always about population. Anyone need more time on that? All right, let's continue on then. So let's talk about an example in which this could happen. So here is a situation where someone at a manufacturing plant is saying, you know, I want my workers to be satisfied with their job. I want them to be satisfied because I don't want them leaving while they're doing productive work for me. So I'm going to try something out here. I'm going to give this idea of whether they pace, the workers pace themselves and determine the pace at which they work, or whether they have to work at the pace in which the machine gives them their work to do. Is their job machine-paced or self-paced? And I'm going to ask the question, in these two different environments, in which environment are the employees more satisfied? All right? So, I'm going to run an experiment. Half of my workers are going to be self-paced, and which group they're assigned to is randomly chosen. The other half of my workers are going to be machine-paced. And we're going to run this experiment for 2 weeks. See how satisfied they are. Then everyone's going to switch. The people who were machine-paced become self-paced. People who were self-paced become machine-paced. And after another 2 weeks, I'll do another satisfaction survey. Find out how satisfied they are. All right? The response variable here, they say, is the difference in the satisfaction scores. So, after 2 weeks, Paul was on the line. How satisfied from a scale from 1 to 100 were you with your job when you were self-paced? 75. And then after 2 weeks of doing machine pace, how satisfied were you? 88. So your score, self-paced minus machine pace, is a negative 13 then, right? Now, he's one person. Can you imagine that we did this for an entire factory? We would get a bunch of scores. And those scores would be negative if they preferred the machine-paced. They would be positive if they preferred the self-paced. What if it didn't make a difference? What if it didn't matter to them? What score would they have? 0. Okay, great. So what is the parameter of interest in this setting? How can we summarize all this data that we're collecting from all these workers? I might say that the parameter of interest is the mean difference in satisfaction scores. Right? Now I want to find out whether one of these two methodologies produces more satisfied workers. I need an hypothesis. I believe it does matter whether they're machine-paced or self-paced. But I don't have an idea which one's better. If I'm going to show that one is better than the other, I need a hypothesis. Remember, I'm about to write the null hypothesis, which is a statement of the thing that I don't believe. My null hypothesis. Let me tell you again, I'm going to go over here. The thing that I believe is that self-paced or machine-paced makes a difference. Can we make a statement of something I don't believe then? That there is no difference. And how would I write that in symbols? I need a parameter. And I need a parameter describing mean. What symbol do we use to mean population mean? What? Mu. Okay? What about mu, if there is no difference? Mu is equal to 0. If I think there is no difference between machine-paced and self-paced, I think that some people are a little bit more satisfied one way, some people the other way, and it's all going to wash out, it's all going to average up to 0. But that's not what I believe, isn't it? That's what I don't believe. This is the null hypothesis. What do I believe? What do I believe? What am I going to say in my alternate hypothesis, the thing that I think is really true? Mu is not equal to 0. Or that this is a two-sided or two-tailed test. Did you hear the logic that had to go on there? I know it sounds really strange. I got to state first what I don't believe. There is no difference. Believe me, and this idea, there is no difference, is going to be a common theme throughout all of this inference testing. Here's this new drug to help with sneezing. I want to prove that it's effective. First, I must assume that it's no different than any other drug, that there is no difference. So that I can then go on with my alternate hypothesis that yes, this reduces sneezing. The proportion of people who sneeze is now lower. All right. Let me see what they wrote on here to make sure I didn't forget anything. Nope, it helps if I take that. Okay. So the parameter of interest is the mean of the difference. Oh, something I did forget. Not only should I describe the parameter, but I better describe the population that I'm studying. This sounds a lot like step 1 of our 4-step process. What is the population we're studying and how are we measuring what we're studying? Population and parameter. So, and then in the second one, state the appropriate hypothesis, and you guys nailed it. The hypothesis, mu equals 0. There is no difference. Mu not equals 0. There is some difference, but we don't know which direction. Great. Let's continue on. Now, the big picture here is that based on the assumptions that we made, the hypothesis that we made, the null hypothesis in particular, we are going to be able to calculate a probability. We get a result, and we say, does this result, is it consistent with our assumption of no difference? Or does it contradict our assumption of no difference by being really, really small? to pull it back to yesterday's analogy, you assume that the coin is fair, and that I'm telling you the truth. And then all of a sudden I get six heads in a row. And you say, that's really low probability. That probability is the evidence against the claim that the coin is fair. Well, the probability that we do in this calculation has a special name, and it's called the p-value. Okay. Again, the p-value is the probability that we get, assuming H0 is true, and we use that p-value, when it's low, as evidence against H0. It's the assuming that I'm an NBA All-Star that leads you to the idea that I'd have to be taller, which is the probability of me being this short and being an NBA All-Star is really, really low. And then you say, oh, that really low probability is the evidence against the claim about being an All-Star. All right, so let's define the p-value. Probability, assuming H0 is true, that the statistic, and remember, when we use the word statistic here, we're saying some number that summarizes a sample. That the statistic would take the value as extreme or more extreme than the one observed is called the p-value. The smaller the p-value, the stronger the evidence against H0. The smaller the p-value, the more the evidence against H0. Smaller p-values are evidence against H0 because they say the observed result is unlikely based on the assumption that H0 was true. Yesterday, I flipped 6 heads in a row, supposedly. What if I had done 20 heads in a row? Very, very unlikely. You know how unlikely 20 heads in a row is? 1 in a million. Is that a stronger piece of evidence that I'm lying? Or to say it in the terms of this H0 thing, is that stronger evidence against the claim that I was telling the truth? Yeah. So smaller p-values are more evidence against H0. But what about larger p-values? What if I flip the coin 6 times and I got 4 heads? That happens all the time, doesn't it? The probability of getting 4 or more heads out of 6 coin flips, pretty common. Probably something like 30%. When you have large p-values, do you have evidence? No. Okay? But let me tell you what we call that. We call large p-values a lack of evidence. This is going to be very tricky in terms of the wording, so I want you to listen very carefully. Have you ever watched any TV court dramas?
Judge Judy.
Law and Order. Okay, I need it to be criminal, not civil. So Judge Judy doesn't count. Okay, Law and Order. Okay, at the end of the trial, what does the foreman of the jury say? The foreman of the jury only says 1 or 2 things. Guilty or not guilty. You know, and those words are very particular. They don't say guilty or innocent. They say guilty or not guilty. Now, the reason why they choose those words that way is if they're guilty, there's beyond a shadow or reasonable doubt, right? They have evidence to the claim of guilty. But what if someone really did it, but they just didn't have evidence? They don't pronounce them innocent. They pronounce them not guilty. They say, we don't have evidence to claim that you're guilty. We call you not guilty. Do you hear the difference between innocent and not guilty? It's a big difference. When we have really small p-values, we say we have evidence that the H0 claim is wrong. When we have really big p-values, we don't say the H0 claim is correct. We just say that we lack evidence that the H0 claim is true, is false. You hear the difference in the language. This is really important. High p-values are not evidence of the H0 claim being true. It's simply a lack of evidence that it's false. I'm trying to read your faces right now, and you're like, Mr. Fedor, I'm not getting it. Okay. No. Let me try some more. All right. Okay, so let's go ahead with back to our workers. Actually, this is a different one. Okay, let's say we did that survey and we found that X bar, the survey of all those workers comparing their satisfaction between being self-paced and machine-paced was 17. Let's say the standard deviation of that data set was 60.
So 17 is...
17 meaning there were 17 points more satisfied being self-paced. And I can imagine that happening, right? You'd rather choose your own pace as compared to having the machine kick out the parts and you have to react to it all the time. Like that episode of I Love Lucy with the chocolates.
Yeah.
Does anyone know what I'm talking about?
That's a good one. I do.
Yeah.
You do, okay.
There's Drake and Josh with the sushi. Yeah.
All right.
No, I'll talk to you. I heard you.
So we collect this data, and we got 17 for our satisfaction score. And let's face it, 17 does not equal 0. It doesn't. But then the bigger question is that 17 just sort of the chance variation that happens with doing surveys? Or does that 17 represent a real difference from 0? So they do a calculation. And they say, based on that mean and that standard deviation, that we could get a value that far away from 0 by pure chance alone 23% of the time. That the p-value of getting x bar equals 17, when our assumption is that mu is actually 0, can happen by pure chance alone 23% of the time. Now what does that mean to us in terms of H0 and HA? Is 23% a low p-value? Is it so low that you think that represents evidence against the H0 claim? I don't think so. 23% does not seem rare to me. In fact, in my mind, I have this line in which I say only probabilities below this line are rare, and that line is 0.05, 5%. 23% is much bigger than 5%. I say that I cannot claim H0 is false. I say that I have a lack of evidence to claim H0 is false. All right? So, in this setting, 23% represents how likely could we get this value by pure chance alone, assuming that the mean of the population is really 0. The interpretation of the p-value. The p-value, again, is the probability that I would get that extreme of value by pure chance alone. And because the p-value is 23%, let me underline the important part here. Okay, happen 20 by pure chance and random sampling. 23%, in my idea, is not strong evidence against H naught. Does it mean that H naught is true? Again, no, it doesn't. It just means that we don't have enough evidence to say H naught is false. Okay? This outcome would occur by pure chance alone about 1 in 4 times. This is not convincing evidence that there's a difference in job satisfaction. Or to put it back into the coin flip example, this is me flipping a coin. I guess I'd have to flip a coin 3 times and I got 1 head. No. Flipping a coin, no, it'd be flipping a coin twice and getting 2 heads. Would you say, boy, that's really unusual? He must have fixed it. Well, except for Jacob, who says, oh, now tails are due. I'm sorry I'm boring you. All right. Okay. So, here's what we say. We say that if the p-value is small enough, we reject H naught. We say if the p-value is too large, we fail to reject H naught. We say that when we reject H naught, that our results were statistically significant. That we didn't think that this happened by pure chance alone. That we really think there is a difference in job satisfaction between self-paced and machine-paced in this last example. If we think our sample, that the result from our sample is too likely to have happened by pure chance alone, we reject H naught. And we say that the result is significant. Now, we fail to reject H naught again because what would happen if maybe our sample size was too small? Maybe by making a bigger sample size, we get a sampling distribution that's a little tighter. And there's less in the tails. And also the probabilities decline. A 17-point difference can be significant if our standard deviation is small enough. In other words, if we collected more evidence, we may be able to reject H naught. But as it is at this moment, we fail to reject H naught. Okay, and again, it doesn't, when we fail to reject H naught, it doesn't mean that we've now said H naught is true. All it says is, we don't know. We don't have enough evidence. There's insufficient evidence to reject H naught. So, to summarize, low p-values lead us to reject H naught. And we try to do that when we reject H naught, we try to do it in context. What does that mean in context? I get a really low p-value in that assembly line example. I say, because the p-value was so low, I reject the idea that there's no difference between self-paced and machine-paced satisfaction. What does it mean to fail to reject H naught? Because the p-value is so high, there is a lack of evidence to suggest that there's a difference. Now, we're going to talk a little bit more about this imaginary line that I've been using 0.05 for. And we're going to talk about its special name and what it has to do with this process. Does anyone require more time on this slide? No? Okay, here we go. So, statistical significance. I've been using 0.05 as an arbitrary value, okay? But our guidelines of when to reject H naught, when to claim something is statistically significant, can vary from problem to problem. We use the Greek letter alpha. Kind of looks like a little fish. We use the Greek letter alpha, and most times we say that alpha is 0.05. Alpha is the value. If you get below that value, we claim statistical significance. p-value is smaller than alpha, we say that the data are statistically significant. And we reject the null hypothesis. And if the p-value is above alpha, we say that we fail to reject H0, and we have insufficient evidence. Thank you. Okay, so let's change the in the nutshell summary to this. When the p-value is less than alpha, we reject H0. And we say that HA must be true in the context of a problem. There really is a difference in satisfaction. When the p-value is greater than alpha, we fail to reject H0, and we say that there's insufficient evidence to say there's a difference. I'm going to circle in context, just to make you understand that whenever we finish our conclusions based on this significance testing, this is, by the way, in box 4 of our 4-step process, that we have to bring the problem that we're actually trying to solve into it. We believe there's insufficient evidence that suggests there's a difference in satisfaction scores. All right. So let's go back to another problem. So we have a manufacturer that produces AAA batteries. Okay, the new batteries are more expensive to produce, but the company would like to be convinced that they do last longer. The old batteries lasted 30 hours, and we would like to test to see whether the new batteries last more than that. So I want to prove that the batteries last longer, so I start with an H0 claim that they last the same. Remember, the H0 represents the claim of that we don't believe. What am I trying to prove? I'm really trying to prove that the mean battery length is greater than 30. Now, we do all the work, and by the way, I'm just giving you the p-value right now. In the next section, next 2 sections, we'll actually go about calculating those p-values. Right? But let's say the p-value ends up being 0.0276. Do we have significance when alpha is 0.05? Now let's see, let's run through that idea again. Is the p-value less than the alpha value? P-value is less than 0.05? Okay, and according to what was on that last screen, when the p-value is less than alpha, we reject H0. Because 0.02 is less than 0.05, we reject H0. What does that mean in the context of this problem? We believe that there's evidence to suggest that these new batteries last longer, that the mean battery length is greater than 30. Okay? What if the significance level was 0.01? We would fail to reject. And how does that sound in that 4th step of the 4-step process? Okay, we can't reject. Okay, in words, it sounds like this. Because our p-value of 0.02 is greater than 0.01, we fail to reject H0. What does that mean in context? It means that there's insufficient evidence to suggest that the batteries last more than 30 minutes. Now, you'll need to be able to regurgitate those words for me on quizzes and tests. Okay, because the p-value is less than the alpha value, and I actually want those numbers to be in your statement. Our result is significant at the 0.05 level. Context. We believe that the mean battery length is greater than 30. There's significant evidence to suggest that the mean battery length is greater than 30. Or if we're rejecting, because our alpha value is really, really low, because the p-value of 0.02 is greater than the alpha value of 0.01, we don't have statistically significant results in the context of this problem. One more time. We believe there is insufficient evidence to suggest that the mean battery length of these new batteries is greater than 30. It's very much a mantra and needs to be memorized as such. I will be giving you a scaffolding sheet in the coming days for you to get that down. Does anyone require more time on this slide? Nope? Okay. Now, let's say in that previous example where the p-value is 0.02. There's a 2% chance, if I remember the definition of p-value, there's a 2% chance that I got my result by pure chance alone. But the batteries were maybe no different, but just by pure chance alone I got that big of a difference. I could be wrong when I make the claim that these batteries are better. Say that one more time. I could be wrong looking at my p-value. My p-value says, how often does this happen by pure chance? By pure chance, 2% of the time, in that last example, or based on that last thing, it could happen. I could flip a coin 6 times in a row and get ahead. You could be wrong by calling me a liar. There could be errors, in other words. Well, exactly, there's two kinds of errors. One kind of error occurs when I say there's statistically significant difference, when in truth there really isn't. When I reject the null hypothesis and I say that the results are significant, when in fact the null hypothesis was true, we call that an error, and we call it a type 1 error. There's another kind of error that can happen. I could fail to reject the null hypothesis when in fact it should have been rejected, when the null hypothesis was false. When I fail to reject the null hypothesis when the null hypothesis is indeed true, that kind of error is called a type 2 error. And you need to be able to tell one from the other. So, type 1 error. Again, when we reject H0, when indeed H0 was true. Type 1 error. When we fail to reject H0 when H0 is truly false, that's a type 2 error. And this is a table that may help you summarize. There's two things that can happen when we look at a sample. We look at a sample and we can either reject H0. When we reject it, and indeed H0 was false, I'll put a star there. That's what we like to have happen. But sometimes, by pure chance alone, we get these crazy samples. And sometimes, with a crazy sample, we'll reject even when H0 is true. Type 1 error. Sometimes we get a sample, and the sample doesn't present enough evidence to say that H0 is false. So, we fail to reject H0. Sometimes we do it correctly, but sometimes we fail to reject the H9 when there really is a difference. And that's the error, and that's the type 2 error. Okay. You ready for an example? All right, here we go. Here's an example. So we're ready, Megan? Good? All right. And that is, a potato chip producer gets shipments of potatoes, and they have particular quality standards. Now they're going to reject a truckload of potatoes if the number of potatoes that have blemishes is too high, if the proportion is too high. Okay, so big semi-truck of potatoes comes in, they go into the semi-truck, they pull samples of potatoes, and they look at a sample of that truckload's potatoes and say, well, what proportion of this sample has blemishes? They do a significance test. Is there statistically significant, is there evidence to suggest that the proportion of potatoes with blemishes is greater than 8%? Because if there's evidence to suggest that, we're going to reject the entire truckload of potatoes and send it back. Now, two things can happen wrong in this situation. Well, there's four things that can happen. I get a batch of bad potatoes, and I reject them. That's good, right? Reject the bad potatoes. It could be a truckload of good potatoes comes in, and I accept them. That's good, right? Yes. But now, what are the bad things that could happen? A truckload of perfectly fine potatoes can come in, but I reject it. I rejected the null hypothesis incorrectly. That's the type 1 error. Now, how are you going to remember which one's the type 1 error? I got this trick for you. Ready? What did I have to look at in order to reject the null hypothesis? I had to look at alpha, the first letter in the Greek alphabet. When I reject using alpha, it's a type 1. Got it? Okay, let's talk about the other bad thing that can happen. I get the truckload of potatoes. If I look at every single potato, I find out the proportion of blemishes is too high. But in my sample, I don't see enough blemishes. I get a weird sample, a non-representative sample. By chance, an unlucky sample, whatever you want to call it. So here's this bad batch of potatoes, but I fail to reject it. And then I go and make my potato chips on that bad potatoes. That's the error 2. That's the type 2 error. I failed to reject when I should have rejected them. Now, both of these type 1 and type 2 errors have consequences. What's the consequence of the type 1 error? That I rejected a bunch of potatoes that were just fine. I lose money. And time. Because there's that batch of potatoes that I now have to get back out of the loading dock and all that kind of stuff. What are the consequences of the type 2 error in there? The type 2 error again, where I got the bad potatoes and I failed to reject them. I've got bad potatoes. And I've got a bad batch of potato chips that go to my customers. And they open up the bag of potato chips and they go, ew. What's that, Sam?
I was just wondering if that's when they're all like green and everything. You know, is that a blemish on a potato?
Yeah, I mean, I think of a bad potato chip as the green potato chip. My mother, she loves the ones that are all black. I don't get it. So anyway, so the type 1 error leads to a waste of money. Type 2 error has the consequence that it may end up, our customers end up getting bad potato chips. By the way, which is the worst error in this case?
Type 2.
Kyle, why is the type 2 error worse?
Because you'll lose customers and money.
Okay. You lose money in the first case, but you lose customers and money in the second case. How many bad bags of potato chips are you willing to tolerate before you never go back to that brand?
2.
2? Okay.
Yeah.
1 or 2 is probably it. You know what so the cost of rejecting a bad batch is high because you lose all those potatoes. But the markup on potato chips is so high, you're willing to risk it. A $1 bag of potato chips contains maybe 5 cents of potatoes. I'm willing to risk 5 cents of potatoes on the upside that day after day after day, Kyle is going to give me 95 cents for a product that's only worth 5 cents to produce. All right. So, we can actually calculate the probability of a type 1 error. The probability of the type 1 error is exactly the significance level that we use to calculate our statistical significance. If I say only if the alpha value, it gets below alpha value of 0.05, that means over many, many, many trials, about 5% of the time, I'm going to reject even though the load was perfectly fine. Let me say that again. Alpha level of 0.05 means that 5% of the time, even when things are perfect, I'm going to reject incorrectly. Built into the system is that one time out of 20 at this alpha level, I'm going to reject a big truckload of potatoes. Do I care? Well, I don't want to lose money, but I'm also more worried about losing customers. Okay. Now, in this particular problem, if we carried out a significance test with the H0 claim that P is equal to 0.08, we could actually think about what the spread of the sampling distribution would be for those potatoes. It would be centered at 0.08. And because we know how to calculate the spread of this, it would actually vary by 0.121. Now, if I actually wanted to calculate how bad does a sample have to be before I reject it, I could actually go and use that Z star value that we talked about in the previous chapter and say, oh, if I get above this level, I think that the population proportion of that truck is above 0.8. It's kind of like this, drawn nicely compared to the way I do it. You've got a distribution of all the p-hats that can come from these trucks. And assuming that the center of this is 0.08, because that's what our H0 is, the area that's got only 0.5% of it above it is up at p-hat is equal 0.0999. That means if I do a sample and my proportion is and my proportion is 0.099 or above, I'm going to reject those potatoes. And sometimes that happens by pure chance alone. How often? 5% of the time. So we say that the probability of the type 1 error is exactly the alpha value, 5%. Which is another way for you to tie alpha and type 1 errors together. You okay with that idea? Manufacturers got to be okay with this, by the way. Sometimes they reject product that's okay, for fear that it gets into the workflow. Okay. So, here's your box points. The significance level alpha is the probability of the type 1 error. 2 errors. Calculating the probability of a type 2 error is much, much harder. In fact, it's so complicated, I'm never going to ask you to calculate the probability of a type 2 error. But I am going to talk about this general idea, and we'll finish that, be able to finish this up today. Okay? So, probability of the type 2 error. The probability that I reject something, that I fail to reject something that should have been rejected, has a complementary component called power. The idea of power is that if a situation has more power, I'm more likely to reject H0 correctly. Power is the probability that given that there really is a difference from our H0 claim, that we actually do reject H0. I understand that this is like a lot of word soup. Okay? Let's get this definition down, and let me show you how it works actually with numbers and with this this particular potato chip example. Three people absent.
I don't know why.
Jason, Taylor. All right. So power is the power of a test is against a specific alternative is the probability that we'll actually reject H0 correctly. Okay. So let's talk about this previous example. In this previous example, we said if we get a batch of potatoes, and essentially if there's a proportion that's 10% or greater in our sample, that's evidence that the population proportion is 8% or greater in terms of the blemishes. So 0.0999 is our threshold. Now I'm going to say, what if we got a batch of potatoes in? And what if that batch of potatoes had a really high proportion of blemishes? Maybe something like, and this is where it goes, a specific alternative. I'm going to give you a specific alternative right now. A specific alternative is 11%. I get this big truckload of potatoes that got 11% blemishes. Now, do I know that? Do I know that the population proportion of that truck of potatoes is 11%? No, because I didn't go through every single potato, typically. But let's say for some magical reason, I know this for this particular load. I get a sample potatoes. Is every single sample potato going to have 11% blemishes? No. There's sampling variation. Samples vary from proportion. The proportion of blemishes will vary from sample to sample. Some will be higher, some will be lower, but there's variation in the sampling. When I do that sampling, I know that the center of all those samples is at 11. I know that some of the samples fall in this area, which is below 0.0999, that magical number that we selected for our threshold between reject and fail to reject. This area here is called the power. Given the specific alternative, the light shaded blue area is the probability that not only that my sample has got enough blemishes that it will reject the whole batch. The red area here, that's the probability of the type 2 error. If I get a bad sample, an unlucky sample, I end up in the red area. And the red area says that even though amongst all the potatoes we have 11% blemishes, my particular sample comes in lower than 0.0999, and I end up accepting that bad batch of potatoes. Power is the probability that we reject the load correctly. Probability of the type 2 error is the probability that I failed to reject even when I should have rejected. Okay, I will not ask you to calculate power. It's a clumsy calculation. But I will tell you this. Power is good. And if you want to increase power, there are only two ways to do it. If you want to increase the power that you actually reject when you're supposed to, the only way to do it is to either increase your sample size, which costs money, or increase your alpha value. If you want to increase power, the only thing you can do to do that is either increase your sample size or increase your alpha. If you increase your sample size, that costs money. If you increase alpha, you have now increased the probability that you're going to commit a type 1 error. So you can't always be right. But probabilities and these statistical analysis, it's not about always being right. It's trying to be right often enough that you can tolerate being wrong. Sometimes you reject potatoes that you shouldn't. It happens. Can you tolerate that? Sure, know what you do? You should charge a lot more for your potato chips that way. You can tolerate rejecting, doing things wrong. You do it all the time. Every day of my life, I'm sure I'm going to do something wrong. I just hope that the thing that I do wrong doesn't have really, really bad consequences. And that's how businesses make their decision. They're going to do some things wrong. Can they tolerate? Can they build enough toleration into the system? All right. So where are we? We're less than 3 minutes left. And I believe... Okay, last point there. The power against the alternative is 1 minus the probability of the type 1 error. I'm sure that'll come up. Oh, and the probability of the type 1 error, they give that as beta. Sorry, the type 2 error is beta. Okay. I believe what we're left with now is just the summary slides. Okay. How big of a sample? So here's some other issues they have to do about how to deal with these issues, and I think that's it. The homework that was given to you yesterday will be due tomorrow. You'll have your first quiz of the second semester tomorrow. All right? I'm done.